Before I get to general monads, I want to start with I/O, so how I/O side effects are handled in Haskell. And before we get to Haskell, let's look at a mainstream language like Java, and imagine we have a Java method with this signature here, a Java method foo that doesn't take an argument and returns an int. And somewhere in the code later we use it. Maybe we use it twice. So in Java, this call of the first call of foo and the second call of foo can very well result in different integers. Even though there is no argument, as long as we don't know what these ... dots do, we have no way of saying that this and this will result in the same. And why? Because in Java, it's perfectly possible that some I/O happens here inside the body of the foo method. For example, inside the body, there could be code that asks the user to input an integer on the console and then returns it. So if we call it here and then again here, maybe at those two occasions the user provides a different integer from the terminal and we get different results. And that also means that we really have to look at the code of this function in order to understand it or in order to reason about it, which makes testing, for example, more difficult. And it also means that, if we evaluate it here and, for example, get the result 13, we can't replace all other occurrences of foo, invocation of foo with the number 13, because, as I said, maybe that's it wouldn't always result in 13. There can be something like console input here, or it could query a website or a database, for example, and that could change between different invocations of foo. Now in Haskell, the situation is very different because Haskell is a pure functional language. So the equivalent signature in Haskell would be something like foo type int. And if then we have the same situation that we encounter foo twice, then I don't know what the value of foo is, but if, for example, I see that here it is 13, then I can be sure that here it will also be 13. And I don't have to look at the dots in order to know that. I don't care what happens here. I know that if I use the same thing twice, it will have the same value. And that's a very important feature that's called referential transparency. And that's a feature that Haskell has. Actually, I'm lying. There are ways, there are like escape hatches to get around that, but we can ignore that. So the vast majority of Haskell programs, something like this will have a fixed value, and that value can never change, and you can rely on that fact. And that, for example, makes refactoring very easy, because I can just replace foo everywhere by 13. Or I could do something like let x equals foo in, and then do the same code as before, now with this local variable x. And I'm guaranteed that this term in line 15 and the term in line 14 will have exactly the same behavior semantics value. And that's this referential transparency. So that's a very nice feature. It makes many things much nicer in Haskell than in other languages. Also, for example, testing, because it means if I have something like that, in order to test it, I must just check that it has the right value. This value can't change. So if I have, this is now not, it doesn't take any arguments, but if I had an argument, then I just have to, I know that if I plug in if I call foo with the same argument, I will always get the same result, which is not true in a Java function, because side effects can happen. So that is very nice and all very well, but of course you need side effects to have an effect on the world. Otherwise, all your program does is heat up the processor. So you need input and you need output. You must make things happen in the world. I mean, you must write results on the screen or read input from the terminal or from a network connection or from a file. If you can't do that, then your program is useless. It doesn't do anything. There's a famous video by Simon Peyton-Jones on YouTube that's called Haskell is Useless, and that is about this thing, that it's beautiful mathematically to have a pure side effect free language, but eventually in the end you do need side effects to make anything happen. And of course Haskell has a way to deal with side effects, and that is the so-called IO type constructor or IO monad. But don't worry about the monad right now. So the equivalent of something like that in Java in Haskell would be foo of type not int but IO int. So IO is a type constructor that takes one argument, like maybe, for example. Maybe is another example of type constructor with one argument, or list is yet another example. So IO is one of these type constructors, and IO is special in the sense that you can't implement it in the language itself. So it's a built-in primitive. And what does this mean? What does this type IO int mean? It means this is a action or a recipe to compute an int, and this computation can invoke side effects. So you can think of it like a cooking recipe or a baking recipe. So it's like a list of instructions what the computer should do to end up with an int in the end as a result. So this type IO int is a computation that can have side effects and results in an int. However, it's important to notice that referential transparency is not broken with this IO. So it's a recipe to produce an int, but when I evaluate this foo, the recipe won't be executed. I mean, the result of the evaluation is just a recipe to produce an int, but no execution is happening. So referential transparency is still maintained. And the only way to actually execute such a recipe, to execute an IO action, is in a main program, in the executable, in the main entry point. So if you compile Haskell to an executable, if you have an executable, then similar to other languages, like Java, for example, there is a main function, and that actually gets executed by the Haskell runtime system. And there's another way, a second way, you can also do it in the REPL. So GHCI also allows you to execute IO, so-called IO actions. So the hello world in Haskell looks like this. So you need a module called main, or in case of the main module, you can also skip the module header. And it must contain a function named main, and the type must be IO unit. So this is a recipe that can do some side effects, and in the end returns a unit, which means nothing. I mean, nothing of value, because there's only exactly one value of type unit. So the only interesting part are the side effects. And this would be hello world in Haskell. Put string line, I can ask for the type in my REPL. So the type of put string line, it is a function. It takes a string and returns an IO action with no interesting result. So the type of put string line, hello world is IO unit. So it's suitable for main program. And I can actually execute it, for example, with cabal run. Now, in my case, I called this hello, so that's specified in the cabal file. So it compiles, and then it indeed has this side effect and writes hello world to the console. I should briefly show you the cabal file as well. So until now, in our previous examples, we only had this one stanza, the library stanza. So we were always just writing Haskell libraries without a main program, without an executable. Now I added this stanza here, this executable stanza, where I just specify the source directory and then which file contains the main module. So I called it hello HS. So here's an exception. Normally, Haskell modules always have to have, the file name must equal the module name. Executables are an exception. So the module name is always main, but the file can have a different name, like hello in this example. I also mentioned that another way to actually execute an I/O action is to do it in the REPL. So earlier I asked for the type of this expression, put string line hello world, but if I just enter it like that, then it will actually be executed in the REPL. So this hello world is the side effect happening while executing this I/O action. So we have one example of an I/O action or way to create one, namely this put string line. Let's look at another one. It's called getLine, and that is of type I/O string. So that means it's a recipe possibly containing side effects that after having executed the side effects will produce a string. And in the case of getLine, the side effects in question is it will wait for user input from the keyboard. So if I execute getLine in the REPL, now it waits for keyboard input, and if I enter something like Haskell and press enter, then I get the result, so the string result, which is the string Haskell. And there are, of course, a variety of I/O actions predefined in Haskell. And we now saw how to write to the console and read from the keyboard. And obviously there are many actions to do all sorts of things that you would expect, like reading files, writing files, opening sockets, reading from sockets, and so on. But obviously, no matter how many predefined actions you have, that will never be enough if you want to achieve something complex. So there must be a way to combine these primitive provided I/O actions into bigger, more complex recipes. One thing we can do is make use of the Functor instance of I/O. So if I ask for I/O, information on I/O, we see the dreaded Monad instance that I'm explaining now, but we also see a Functor instance. Functor is a very important type class in Haskell, and it in principle only has this one method that's important. This one, the second one, is just for convenience. So if you have a functor type constructor, then you can turn FA into an FB if you have a function from A to B. So we are now only interested in the case where F is I/O. So if we specialize this to I/O, you see that using fmap and given a function from A to B, we can turn an IOA into an IOB. And how does that work? Well, an IOA is a recipe containing side effects that in the end produces an A. So how do we get an IOB out of that? Well, we take the same recipe with the same side effects, but then before eventually returning the A, we apply the given function to it and then return the result of applying this function to A to get the B. So as an example, if we import data.character from the standard libraries, we have the function toUpper, which converts a character into its uppercase version. So for example, toUpper small q, sorry, the character is not double quotes, it's single quotes, so to upper Q gives me the character capital Q. Now if I want to apply that to strings, I can use the map function on list, because strings in Haskell are just lists of characters. So if I map the to upper function over a string, for example Haskell, then it gives me the string where now all the characters in this string have been converted to uppercase. Okay, so this map to upper function is a function from string to string. Remember, a string is just another name in Haskell for list of character. So that means I can use that in combination with fmap. So if I have fmap and as function from a to b, so in this case a and b are both string, and as function from string to string I use this to upper. And then getLine, I again get something of type IO string. So getLine was of type IO string. The function I'm fmapping is from string to string, so I again get something of type IO string. And we can try that out and see it in action. So if I execute this in the REPL, it waits for user input, and if I now provide Haskell and press enter, we see that the result is now not just a string I entered, which would be the result of getLine, but this function, this map to upper, has been applied to a result before returning it. So we get Haskell all capitals. So that's one way how we can take existing IO actions and turn them into new IO actions. The second way is provided by the by this character. I don't actually know how to pronounce it. greater than. That just chains two IO actions together, ignoring the result of the first. So for example, we can do put string line hello, and then this operator put string line world. And if we execute this, simply both actions will be performed in sequence. So I think it's called a sequence, the operator. And in this case, the put string line only has a unit result, but of course this first one could also be a function that has a non-trivial result, but this operator simply ignores it. So given these two recipes, what the sequence operator does, it just basically sticks the recipes together. First performs all the side effects from the first recipe, then throws away the result, and then just attaches the second recipe. So that's one way. Then there is a very important operator which does not ignore the result of the first one, and that is called bind. So it's like this. And if we look at the type of bind, we see this monad constraint, but we can ignore that for now and just think of IO. So what that says is, if I have a recipe that performs side effects and returns an A, and if I have a function that given an A gives me a recipe that returns a B, then these two can be combined to a recipe that produces a B. And how does that work? Well, if we have this IOA, we have a recipe to produce an A, so we can perform these side effects that will eventually give us an A. And then once we have this A, we apply this function here to that A and get a second recipe now of type IOB, and we simply execute that, and in the end get a B as a result. So as an example, I can apply this to getLine and put string. That has exactly the right type. So getLine is IO string, and then put string line has type string to IO unit. So if I combine these two with this operator, I get something of type IO unit. And what does it do? It will first execute the getLine, which will return a string, then plug that string into put string line. So it will put the string line that was just entered out on the console. So to demonstrate, if I do this, getLine put, it must be bind put string line. So now the getLine is executed. If I enter Haskell, now this results in the string Haskell, which is passed on to put string line, and then put string line executes its side effects and writes Haskell to the console. There's another very important way to create I/O actions, and that is to produce recipes that immediately return a result without performing any side effects. And that is done with a function called return. So if I ask for the type of return, again, it's general for any monad, but we can just think I/O. So return has type A to IOA. So given an A, it produces a recipe that can contain side effects and eventually produces an A. And in the case of return, the recipe will simply not perform any side effects and immediately return the given A. So for example, I can do return Haskell. And now I have to give a type annotation because otherwise I wouldn't know what monad this is. So it's IO string, and it immediately returns the string Haskell. Returning back to our main program, using these operators that I just explained, we can now write relatively complex I/O actions. For example, I can define an I/O action that will ask for 2 strings and then write the result of concatenating those 2 strings to the console. So let's call that, I don't know, a bar. So it will have type IO unit. So what do? I do a get line to read the first string, and I bind it to a function. And now I will use lambda expression. So I call the first element, read in element S. And now I format it a bit special, but in Haskell you have a lot of freedom when you format your code. So now I bind this to a second get line, and now I bind a third action. So let's call the result of this second get line T. And now after I have this S and T, I do a put string line of S concatenated with T. If I go back to the REPL, okay, I just get a warning that it's defined but not used. So for example, I can, if I want to get rid of that warning, I can use bar here in main. Okay, and now if I execute this new executable, now with bar, so now it waits for the first input. So let's say 1. Now it waits for the second input, let's say 2. And it returns, it doesn't return anything, but it writes the concatenation of the 2 to the console, 1, 2. So you see that using these handful of combinators, basically just the bind and the return, I can write arbitrarily complex I/O actions. And this is enough for us now for our purposes, because we won't really need the I/O monad. Maybe much later in the course when we talk about actually deploying Plutus contracts to the testnet. But everything else, for everything else, we won't need I/O. But it's an important example of a monad, so I wanted to start with this. Now for a while, let's completely forget about I/O and let's just write pure functional Haskell using the maybe type. So the maybe type, for those that don't know, is one of the most useful types in Haskell. So it's a type constructor that takes one type argument, and maybe A is often called something like optional in other programming languages. So it's an optional A. So there are 2 constructors for this type, nothing and just, taking an A. So a maybe A can either contain an A with a just constructor or nothing. And let's import text read, text read, read maybe. Right. In Haskell, if you want to pass a string to a value that has a read instance, that is normally done with the read function. So I can, for example, do read 42, and tell the compiler I expect an int, and it gives me, it passes the string 42 into the int 42. But read is a bit unpleasant, because if I have something that can't be passed as a string, then I get an error, and that's not very nice. So that's why I imported this read maybe. Read maybe is very similar to read, but it in the case where pass is not possible, it will return a nothing. So if we replace this read with read maybe, and now the return type is maybe int, we get just 42. But if we again try that with something that can't be passed as an int, then we won't get an exception, we get a nothing. I created a new Haskell module called maybe, and let's say I want to implement a function, doesn't matter, let's call it foo, that takes 3 strings and returns a maybe int. And the idea is that the function should try to pass all 3 strings as ints, and if that's successful, so if all can be successfully passed as ints, then I want to add those 3 ints and return the sum. And if one of the passes fails, I want to return nothing. So one way to do that, and I mean this is just plain elementary Haskell, so I try read maybe, I apply it to the first string, and now there are 2 cases. It could fail. So if I already can't pass the first string, then I can immediately stop. Then I don't even have to look at the other 2. But if that succeeds, let's say that's k, I call that k, so k is now the integer that's passed from x, I can try to pass the second one. And again, I have 2 cases. This can fail, in which case the whole computation should return nothing, or there can be a successful pass, so I pass it as a just L. And now I can look at the third string, and again 2 cases, nothing, in which case I fail, or success. Let's call the result M, and now I have successfully passed all 3 strings as integers, and now I can return just k plus L plus M. So I can try whether that works. So if I have foo 1, 2, 3, I get just 6. So this is passed as 1, this is 2, this is 3. All 3 passings succeed. So I can add 1 plus 2 plus 3 and get 6. But if one of those can't be passed, then I get nothing. And of course, if I get nothing. Okay. But if we look at this code, we see that we repeat the same pattern 3 times, and it's always very similar. So we have something that is a maybe. This read maybe x, read maybe y, read maybe z. And then depending on the result, we always have to consider the 2 cases, that it's nothing or just. And in the nothing case, we always fail with nothing. And in the just case, we carry on with the rest of the computation. And as Haskellers, we hate repetition like that and a lot of noise. So, I mean, the thing we want to do is very simple. We want to pass these 3 strings and add the result. But with all these cases and always having to take care of the nothing case makes it very noisy and very ugly. So as a Haskeller, the natural tendency is to try to abstract away the pattern we have here. And one way to do that would be to define something like bind maybe. Given a maybe a, and the function from a to maybe b, we get a maybe b. And how would we implement this bind maybe? Well, if it's nothing, then we don't even care about the function. We immediately say nothing. But if it's just x and we have the function f, then we apply f to our x. And this is exactly what we did 3 times here. So to demonstrate the usefulness of this bind maybe operator, we can now write the same function again, our foo, but now using this bind maybe. Okay, so first we apply to read maybe x, and now we use bind maybe, and I write that in inline style to make it the pattern nicer. And if we successfully, so in the nothing case nothing, this is now encoded here in this bind maybe. But if we succeed, let's call this k. So then I can do read maybe y, use my new bind maybe again. And if it succeeds, I call the result L. And a third time. Call the result M. And in that case, I just do just k plus L plus M. Okay, now I can try the same things I tried before with foo prime, and I should get exactly the same results. So in the case where all 3 passes succeed, I get the sum, but if one of the 3 can't be passed, I get nothing. So we see that by introducing this bind maybe, we capture this pattern, this very common pattern that you often encounter when you use optional values of type maybe, that if it's nothing, you want to immediately stop. It doesn't make sense to continue. But if it's just something, then using the value of this something, you can continue. And this is captured in this bind maybe function. And we see that using this, we can write the original foo function much nicer, in a much nicer form. So we don't have this dangling case statements any longer and all this noise with the nothings, because this is now encapsulated, abstracted away in this bind maybe function. This does exactly the same as the foo did, but it's much more compact and the business logic is much clearer. We see we try to read these 3 strings, pass them as ints, and if everything succeeds, we return the sum. So there's far less noise now by using this bind maybe function. And what that bind maybe does is it encapsulates the idea that we have something of a maybe type, and if that something is nothing, the overall result of the computation is nothing. And if it's just, then we continue with the value of this just. And if you think about it, that's a bit like exceptions in other programming languages. If you think of nothing as an exception, then the normal behavior of exceptions in other languages is that as soon as an exception is thrown, you immediately stop with the computation and return the exception or bubble the exception up. And this here now behaves very similarly. As soon as we encounter nothing, we immediately stop with nothing. And if not, we carry on. And this pattern, this idea, this exception-like behavior is captured in this bind maybe function. And using that, we can write the original logic very compactly. Another very useful type in Haskell is the either type that takes 2 parameters, 2 type parameters A and B. So If I ask for information for either, then we see it has two constructors like maybe, but both carry value. So an either AB can either carry an A or it can carry a B, and the two constructors are left and right. So for example, I can have left Haskell. It can be of type either string int, but I can also have right 7 of the same type. I created another module where called either, where I basically just copied what we had for maybe. And if we take this exception analogy a little bit further, then one issue with maybe is that if we do nothing, so if we return nothing, in analogy to throwing an exception, then there is no error message. It's just nothing. It just fails without any indication of why. So if we want something like that, then we can replace maybe with an either type, where right corresponds to just and left corresponds to an error, like nothing did. But now we, depending on what type we choose for the first type parameter A, we can have a type of error messages. For example, we can use string. And the read maybe returns a maybe and not an either. So let's first define something. Let's call it read either. So read maybe has type read a string to maybe a. That would be the type of read maybe. But now let's replace this with an either string a. And we can implement this in terms of read maybe. So given a string, we just check what read maybe tells us about this string. So if parsing is not possible and we get a nothing, we can now return a left and pick some error message. This is now, it doesn't matter what we say, but I can say something like can't parse and just append the string, the given string. And if we can successfully pass to an A, then we return a right A. So we can try this out. So read either 42, either string int. That succeeds and we get right 42, where before with read maybe we got just 42. And if we pick something that can't be passed, then instead of just nothing, now we get a more informative error message, can't pass this. Okay, and using that, we can now rewrite our foo in terms of either string int. So, and we replace all the read maybes with read eithers. Now, of course, the cases change. Now, instead of nothing and just, we get left or right. So if we get left error message, well, we just stop with the same error message. And if we get right K, we continue. Same here. Left error message, left error. And if it's a right, we continue. And once more, left error, left error. And if we get a right, we continue with right. That would compile, but okay, let's see. So let's try this out. So foo, what were examples if we have 1, 2, 3? We get right 6, but now if one of the arguments can't be passed, then okay, now maybe it's correct, but we don't see much. So if I write something, then now it doesn't simply fail, I get a nice error message. And if I have an error in one of the, or something that can't be passed as an int in one of the other arguments, it works accordingly. And of course, we have the same problem again that we had with maybe, that we have these dangling case statements and a lot of repetition, a lot of boilerplate, because we always follow the same pattern. We always pattern match on the either, and in the left case, we simply return again the same left with the same error message that we got. So we immediately stop, don't continue, and instead return the error we got. And in the right case, we continue with the rest of the computation. And there's a similar solution again to what we did before. So let's define a similar helper function that we call bind either. Where we replace each maybe with a either string, and now try to abstract away this pattern that we repeated 3 times here. So if we get left of an error message, we simply return left of the same error message. And if we got a right X, then we simply continue plugging X into the continuation of our computation. And now in the same way as before, I can rewrite this foo in a much nicer form. I just have to replace each bind maybe with bind either. And of course here I have to use read either instead of read maybe. And here write. And now the same should again work if we use foo prime. So if all goes well, we get right, and if something can't be passed as an integer, I get a nice error message. And the same I said before is again true. So by introducing this little combinator, I abstract the pattern away that we repetitively used here, and the business logic becomes much clearer. And the code, incidentally, is very similar to what we had for maybe. It's almost the same, except that instead of bind maybe, I'm now using bind either. Instead of read maybe, I'm now using read either. So far we have looked at 3 examples: IOA, maybe A, and either EA or either string A. And IOA represents plans that can involve side effects and when executed produce an A. And maybe A and either string A represent computations that can produce an A but can also fail. And the difference between maybe and either is just that maybe doesn't carry any error message, whereas either does. Now let's look at a completely different example that captures the idea of computations that can also produce log output. We can represent that with a type. Let's call it writer A. And let's just say it is a constructor that takes 2 arguments, an A, which is our result, but also a list of log messages. For simplicity, let's do it like this. Okay, and let's actually we can arriving show. And as an example, can define a function number from int to writer int. And given a number n, integer n, we just produce that number, and as log output, we just, it doesn't matter, but we can, for example, just say number and then show n. I can try that out in the REPL. So number 42 is, so we have the 42, the result, and this log message. And now let's do something similar as before. this foo function. So say we have 3 logging computations that each produce an int, and we want to compute those 3 computations to one that adds the 3 ints. So foo x, y, z, or let's pattern match, writer kx, writer ly, and writer mz. What can we do? So the overall result is k plus l plus m. And what should the log message be? Well, so we know each of the x, the y, and the z is a list of strings. So I probably should, rather following the Haskell convention for lists, call it x's, y's, and z's. And I can, for example, just concatenate those 3 lists. Okay. And I can try this also out. Let's say foo number 1, number 2, number 3. And I get the expected result. So I get the sum as result, and I get these 3 log messages. Let's write another useful function. Let's call it tell, and it should just get a list of log messages and produce a writer unit. So one that doesn't have a useful result and just cares about the log messages. And I can just define that like so. Right, the compiler tells me I can write it simpler like this as well. And so I could make this example a bit more interesting. I could add another log message. So let's say let s equals k plus l plus m, and write us equals tell sum show s. And now I can actually do it like this. And if I run the same example again, now we have an additional log message here that tells us the sum is 6, and we have the result. So the idea is we see we can again combine computations, several writer computations into a bigger computation. And the idea here is that we have to concatenate the log message from each computation in order to get the overall log message. And as before, we can write the function bind writer. So given a writer that produces an A and a function from A to writer B, we can combine those to a writer B. What do we do? Again, I can pattern match against the first one. Okay, and how do I do that? Well, now I have the result A of the first computation, so I can plug this A into the function f to get a writer B. So I can say writer bys equals fa. And now I can produce the result. So the result of the computation is B. And what are the log messages? Well, the xs from the first one plus the ys. And now using that, I can rewrite my foo using this bind writer. And make it much nicer. So I start with X, bind writer, call the result K, then Y, bind writer, call the result L, Z, bind writer, call the result M. Now tell some K plus L plus M. But actually I should I can also use a let here. So let S equals K plus L plus M in tell sum is show S. Bind writer. And here I don't care about the result because tell doesn't produce a nice result. Now writer the sum and no u log message. I must remove the rest here. Okay, and now what we did with foo before, we can do with foo prime, and we get the same result. And admittedly, it's even longer now than it was before, so or at least not much shorter. But I think that it still is much nicer than the foo version. We don't have to do this pattern matching to extract the log messages from the 3 input computations. We don't have to explicitly combine the log messages, where we could make a mistake and forget one or get the order wrong. Instead, we basically abstract all of that away and can just concentrate on the business logic. And apart from this part here where we use this additional tell, this is also very similar to, if you remember, what we did with maybe and either. So the code looks very much the same. So as before, we have this business logic. We have 3 computations, and that somehow result in an int, and we form the sum and return the sum. But note that the special aspect of these computations is completely different. In the maybe and either case, we captured the notion of failure, that something can go wrong. Whereas here in the writer case, there is no failure, but we have additional output, these log messages that we combine. So the bind maybe and bind either encapsulated the logic that if you want to combine 2 computations that might fail, and the first one fails, then the overall computation fails. Whereas if the first one succeeds, you can take the result to continue with the second computation. Here, the bind writer captures a different logic of sequencing computations, namely the logic that if you want to sequence 2 log output producing computations, you simply combine the individual log outputs. Now I think we are in a position to explain what a monad is. So going back at the 4 examples, what did they have in common? Well, we had a type constructor with 1 type parameter in every case, IO for real-world side effects, maybe for computations that can fail, either string for computations that can fail with an error message, and writer for computations that can produce lists of string as log output. And for all 4 of these examples, we had a bind function. So in the case of IO, it was this operator It took an IOA and something A to IOB, and you can combine the two to an IOB. And we had very similar functions that we called bind maybe, bind either, and bind writer for our other three examples. And they always had the same shape. You take a computation of the type of computations you're considering, it results in A, and then a function from A to another such computation that results in a B, and you can bind the two together to a computation that results in B. And how this bind works depends on the case. In the case of I/O, it's built-in magic, but you can think of it as just combining the two plans that describe the I/O actions to take during execution. And in the bind maybe and bind either case, the logic is that if the first computation fails, then the combination also fails. But if the first computation succeeds, you continue with the second one. And in the bind writer example, the logic of bind was to just combine the lists of log messages from the two parts of the computation. And that is the main idea of monads. It's a concept of computation with some additional side effect. It can be real-world side effects, it can be failure or failure with error messages, it can be producing log outputs, and there are various other examples that I didn't mention. And the possibility to bind two such computations together. And how the bind works depends on the computation you're considering. There's another aspect that I briefly mentioned in the case of I/O, but not for the other examples. Another thing that we can always do, whenever we have such a concept of computation with side effect, we also always have the possibility to produce a computation of this type that doesn't have any side effects. So I talked about return in the I/O case. So given an A, you can turn it into an IOA, and that is simply the computation that immediately returns an A and has no side effects, no real-world side effects. In the case of maybe, we have the just constructor of maybe. So given an A, just A is of type maybe A, and it doesn't fail because it's not nothing. So it doesn't make use of this special possibility to fail. It doesn't fail. Same for the either case if we use the right constructor. So either string represents computations that can fail with the string error message, and if we use the right constructor, we have such a computation, but it doesn't fail. No error message, it has an A result. Finally, for writer, there is no short way to write it down. We could, for example, define a function, return writer or something, but I just wrote it down here as a lambda term. So given an A, we just produce writer A with an empty list of log messages. So given an A, we can produce a log message producing computation of type A that doesn't make use of this possibility to produce log messages and simply doesn't log and immediately returns the result. And the combination of these two features, the possibility to bind two computations together and the possibility to construct a computation from a pure value without making use of any of the potential side effects, this is what defines a monad. So if we look in the REPL and ask for monad, then we see the bind here. So in the monad class, we have this bind. So monad is now type constructor M. So where we have seen various examples, I/O, maybe either string, writer. And we have this bind operator. So taking a computation that results in A and a way to turn an A into a computation that results in a B, combine those two parts to a computation that results in a B, and the return that takes a pure value of type A and turns it into a side effecting computation, where the intuition always is that the M allows potential side effects, but in the return case, it doesn't make use of this and just wraps this pure value into such a computation. We see here that we also have this operator that I explained in the case of I/O, but that can easily be defined in terms of the bind. So it's just given for convenience. And what it does is it just throws away the result of the first computation when it considers the second. So in other words, you can easily define it from bind by using the constant function here, the function that completely ignores its argument and always returns a fixed MB. In order to, once you have bind, you also get this sequence operator. There's another technical computation. We see that monad actually has a superclass applicative. So every monad is applicative. And if we ask what applicative is, we see it has a bunch of functions, but actually you only need the first two. And we see pure actually has the same type signature as return. And then there's this one, which looks a bit more complicated. But the fact is, once we have return and bind in a monad, we can easily define pure and this operator that's called pronounced app. So pure is just return, and app there is actually a library function that automatically, given a monad, implements this. When we see that applicative in turn also has a superclass functor, and I mentioned that before also in the context of I/O, functor has this fmap class method. So given a function from A to B, we can turn an FA into an FB. The prototypical example for functor is lists, and then fmap would just be map. So given a function from A to B and a list of A's, you can turn it into a list of B's by simply applying the given function to each element in the list. And we saw that we also have fmap for I/O. And again, once you have return and bind, it's easy to define fmap in terms of return and bind. So there is a general pattern. So basically, you never, if you want to define a monad, you always define return and bind, and just to make the compiler happy and to also give instances for functor and applicative, there's always a standard way of doing that. So we can do this in the example of writer. So if I want to define a monad instance for my writer type, I need functor, applicative, and monad. But in almost all cases, you never do that explicitly. So I leave that open for now. So all you normally do is you define return and bind. So bind is just our bind writer, and return is the what I wrote there in the comment earlier. So we return by simply returning the A and giving empty list of log messages. Right, and given this, the standard way to implement functor and applicative is to use helper functions from the prelude from control monad. And there's something like lift m that always, so that basically makes use of return and bind to implement fmap. And for applicative, we need this pure, which we can just use return. And then we need this app operator. And there's something in similar to lift m, there's something called app in control monad that does that. Again, using return and bind, it implements this. So this is the standard pattern. If you implement a monad, you implement return and bind, and then for the functor and applicative instance, you just use this these helper functions. Lift m for pure, you use return, and for this app operator, you use app. And that should compile. Right, so now we have by hand implemented a monad. I don't have to do the same for maybe either and I/O because they are all already monads defined in the prelude. So there I don't have to do anything. And now that we have that, we can actually try to understand why this is useful. I mean, first of all, it's always useful in general to identify a common pattern and give it a name. Just to name things somehow makes the importance of the concept clearer. And so it's always a good thing to identify that this is an important concept, an important pattern that happens all over the place, and then explicitly describe the pattern and give it a name. So that's one advantage. The second advantage is just that, I mean, we had to came up with all these names, bind writer, bind maybe, bind either. And now by using the type class, we don't have to remember all these different names for the different examples. We can always use return and bind. And finally, maybe the most important advantage is that there are lots of functions that don't care which specific monad instance we are dealing with. They just work for all monads. So we can write it once and for all monads, and then reuse it for specific examples. So both in the maybe and in the either and in the writer case, I had this thing where I took 3 computations that represent integers, and then I returned the sum of them. And I can now, let's call it 3 ints, do that for all monads, once and for all. So I get an mint and an mint and a third mint, and turn it into an mint. And mx, my, mz. And how do I do it? Well, I take the first one, call the result, for example, k, bind that to the second computation, call the result L, bind that to the third computation, call the result L. Now I can define the sum. And now I can use the return of the monad to return the sum. I mean, I wouldn't need the let here. I could also do that inline, of course, which I basically did in. I can also do it like this. But for reasons that will become clear in a second or in a minute, let me leave the let here. And if we now look, if we go back, for example, to our maybe, we see this is now almost exactly the same code that I wrote here, except that instead of bind maybe, I'm now just using the bind operator that I have for every monad. So we can now rewrite this. If I import this, then I have the 3 ints function. So I can now write a third version of this foo. So now using the 3 ints function that I defined in the monad module, I can turn this into a one-liner, read maybe x, read maybe y, read maybe z. Trying it out. So foo 1, 2, 3. And again, I get just 6. And if one of those is not parsable, I get nothing. I can do exactly the same for either. If I also import this 3 ints function, so in this case it's 3 ints read either x, read either y, read either z. And again, I can try it out. 1, 2, 3. And we get right 6. And if one of them is not parsable, I get a error message, appropriate error message. Writer is a little bit, I can't, because of this line here, because of this additional log, it's not exactly the same. But if I am happy with not doing this log, here then it's even simpler, because this is immediately an instance of the 3ins. So I must import the module. So that would work, but of course that's a bit cheating, because now I don't have this, but I can get that as well. So I can simply use bind again. So if I want to do that, I do have to give the arguments. I see. Okay, so I get the sum as a result. And now I can do the tell sum show s. The tail doesn't have an interesting result, so I could write unit here, or I can simply ignore it. Or I can use the sequence operator, which is made for exactly this case where I'm not interested in the result, and then return s. And again, if I run foo double prime, okay, sorry, I have to do number 1, number 2, number 3. Then again, I get the same as before. So we see that now with this 3ins function that we defined once and for all for arbitrary monads, I can write all this specific code that I did for the various cases, just reusing this function. So that's one of the, or maybe the biggest advantage of actually having this monad class. There's if you look into the control monad module in the standard Haskell prelude, there are many useful functions that you can use for all monads. And so you have to write them once and for all in Haskell, and then you can reuse them over and over again. So let's go back to this monad module one last time. So yeah, there are, I mean, the way I think about monads, it's a monad is some sort of computation with a side effect or a special feature or a special power. It's like a superpower. And so in the case of I/O, the superpower would be having real-world side effects. In the case of maybe, the superpower would be to be able to fail. In the case of either, the superpower would be to fail with an error message. And in the case of writer, the superpower would be to log messages. So you have this computation, you have a type that represents computations with some special features, some special power. And what turns this into a monad is the existence of return and bind. So return says you must have a way to, given a pure value A, you must be able to produce a computation of this type with return value A that does not make use of the superpower of the special feature. So it's an I/O action that doesn't have any real-world side effects, or a potentially failing computation that doesn't fail, or a potentially logging computation that doesn't log. So that's return. It turns a pure value into such a value in that type of computations. And bind allows you to chain several computations of this type together. So giving given one, and a way to given a result of the first one, produce a second computation, you can use bind to bind those two together to one. And that is, of course, crucial if you want to assemble a large, complicated computation. So you have like simple primitive ones, and using return and bind, you can assemble them into arbitrarily complex computations. And there is this slogan in the Haskell community that Haskell has an overloaded semicolon. And the explanation for this is that in many programming languages, in imperative programming languages, you write lines of code, and at the end of the line you have a semicolon. And then basically what that does is it executes one after the other, and the different statements are separated by the semicolon. But what exactly the semicolon means somewhat depends on the programming language. For example, there could be an exception, in which case computation or execution would stop at the spot where the exception happened and wouldn't continue with the next lines. Or there can be other things that could potentially happen. And in a sense, this bind is like a semicolon. So it binds different statements of computations together, like a semicolon does in an imperative language. And the cool thing about Haskell is that it's basically a programmable semicolon. So we can say what the logic is of binding two computations together, depending on the monad. Again, in the case of failure, the logic is that if the first computation fails, the whole thing fails. In the case of logging, of writer, the logic is that you simply combine the individual lists of log messages to a long concatenated list of log messages. So each monad comes with its own semicolon, basically, its own bind that tells you how to combine two computations. One last thing that needs to be mentioned is do notation. Because this is so common and monadic computations are all over the place, and we always have this pattern. So we do a bunch of monadic computations and we bind them together and give the result a name. There's special notation for this in Haskell that's called do notation. It's just syntactic sugar, so it doesn't add any more power to the language. You could write everything simply like this. But actually how it would normally be written in Haskell would be using do notation. So let's write the same function again, but using do notation. And then this would look like that. So there is a do keyword, and then instead of writing it like this would be written like so. So which has far less noise than this, but it means exactly the same thing. So the compiler will simply translate this do version into this. So whenever we want to bind and use the result, give a name to the result, we write it like this. So the computation is on the right of this arrow from the right to the left, and on the left is the name that we give to the result of this computation. And then we don't have to explicitly use the bind operator. We can just write a new line. And now in the following lines, the K and the L and the M will be available, so I can use it here for the return. And another thing you can do is let. So, I said earlier that I want to leave it like this. So I would do that like this. So you can also use let statements in a do block, and note that the in keyword that is normally needed in Haskell. So normally in Haskell it's let in, but in a do block you don't need the in. So so normally you would, in this case, instead of using explicit binds, you would use do notation. For shorter expressions, it's more or less a matter of taste. So you can always use do notation, but you don't have to, and often if it's like one or two computations, then people also use explicit binds. But as I said, it's a matter of taste. So if we once more go back to our writer example, let me just write this here in do notation instead, this foo double prime. So S goes here, then just the tell. Okay, and if I'm not interested in the result, I just can just write it like this. So I don't need the inverse arrow and the name if I'm not interested in the name, and just do it like so. And if I reload and run this again, now with the do notation, implemented with do notation, I get exactly the same result. So this is how I would normally write it. And that's monads for you. So hopefully now you have an idea how monads work, what they mean. And there would be a lot more to say about monads. So for example, we have now seen examples how to do failure in pure code and logging and also I/O. Not in pure code. I/O is not pure, but the other examples were all pure code. And how to use the monad instance of these examples to basically handle all of them uniformly using, for example, do notation or bind and return explicitly. But often, so we have these special features like failure with error message, logging messages, and so on. But often you are in a situation where you need several of these effects. So you want failure and log messages, for example. And that is also possible in Haskell. And there are a variety of approaches how to do that. One is called monad transformers. So with using so-called monad transformers, one can basically build custom monads using these transformers. So you can just say, I want failure and I want log messages, and then you use the monad transformer library to build a custom monad that has exactly the features that you want. But there are other approaches. One is called effect systems, which has a similar objective. So you basically want to tailor make monads that have exactly the features you want them to have. And that is incidentally what Plutus uses for important monads, in particular the contract monad in the wallet, and also the trace monad that is used to test Plutus code. And the good news is that you don't have to understand effect systems to work with these monads. So it's enough, so for example, to work with the contract monad that you use to define Plutus code that runs in the wallet, off-chain code. You must just know that contract is a monad, which, for example, tells you that you can use do notation. And you must know what special superpowers, what special features this monad has. So, for example, in the writer monad, we have this tell function that's specific to the writer monad. And in the case of maybe or either, we can basically fail. So we have something like we can throw exceptions, which would be nothing in maybe or left in either. And similar, there is a list of things that you can do in the wallet contract monad. So all you have to know is basically how monads work in general, how you can chain statements or computations together using bind or do notation. And then for a specific monad, like the contract monad, the wallet monad, you have to know what specific features this specific monad offers. So that is what we will look at next. So we will look at the contract monad and see what this specific monad can do.